$66 QLA. Nice.
Welcome everyone to this week's edition of our FRC workshop series. We've had a lot of great workshops over the last couple of weeks, and tonight I know we're in for another really good one. We want to welcome someone from Project Bucephalus. This is Lewin. Lewin, you might want to turn off the sound.
I don't have sound on here. Yeah, but there's no sound coming out of here.
Okay.
I don't know where it's coming from, because my computer's completely muted.
All right, well, here we go. I will just turn it over to you and enjoy tonight's session.
Okay, so now I need to share. Is that the right screen? I don't see it on. Okay. So, hi guys. I'm Lewin. I'm going to be presenting Fail Fast, Fail Cheaply, prototyping from game release to final design. Just a bit about who I am. My name's Lewin Mulvihill. I've been involved in FIRST for about 8 years now, FLL for 4 years, mostly on the Knights at St. Knee. I've been on 5985 for 5 years now, 4 as a student, technician, mechanical and pneumatics, and now I'm a mentor. I'm also studying first year mechanical engineering at the University of Wollongong. And yeah, feel free to contact me if you have any questions after. My email is at the very end of the PowerPoint as well, so you don't have to worry if you don't catch it here. So in this webinar, we'll cover what is prototyping, why prototype, our process, so 5985's personal process of how we prototype from game release to our final design, and then some examples of our prototypes over the years from 2017 through to now. So what is prototyping? It is the first version of an idea or a concept. So essentially, it's the thing that you build before you build the actual thing. There are 2 main types. There's a concept selection, and then there's parameter evaluation. So concept selection is essentially where you're pitting 2 mechanisms against each other. So for the example there, I've got a flywheel shooter versus a catapult shooter. So you're testing each mechanism to see which one works the best. And then with parameter evaluation, it's after once you've picked your concept, so you've gotten through concept selection, in this case, you picked flywheel, you go into parameter evaluation. So you've got different parameters and variables in that one design that you can change. So there's the compression on the flywheel and then the speed of the flywheel. And yeah, in the end, FRC robots are just advanced prototypes. You're not going into industry with any of these. So yeah. Why prototype? So it allows for iteration of a design to quick iteration of a design and like find issues that need to be resolved. It's an important part of the design process because it allows you to test and prove lots of ideas really quickly. And then because you're doing it quickly, you're failing quickly and learning quicker how to design a better system to like circumvent those failures and breakages. You'll easily be able to find what mechanisms work best. I can't remember where I saw it, but someone put it nicely. The mechanisms will prove themselves. So if you're prototyping well, you'll easily be able to find whether a flywheel or a catapult works better in the data you get from it. So you keep running them, and one will hit 80% of the shots and one will hit 90% of the shots. And then you'll go, oh, well, obviously this one's better because it's doing better. And it also allows you to figure out things that are harder or easier than they look. So especially with this year, in like indexing the balls, so a hopper in your robot, moving the balls into your shooter. So we looked at it and we went, oh, that's relatively easy. But the skin on the balls is really grippy. And so the balls just want to stick to themselves and just mess about and not do what you want them to do. So our process. So on the game release day, so day 0, at 2 a.m., we get the game manual and the game animation. So we will read the rules. So game pieces get revealed, and you'll naturally start thinking about possible ideas and mechanisms. But you want to keep those ideas to yourself until you brainstorm as a team. This way, you don't have people polluting other people's ideas. So example, little Timmy has thought about one idea, and he's gone and told everyone else about his idea. Everyone else that he's told is now going to be going, oh, Timmy's idea is great, and not think of their own ideas because they'll have been polluted by Timmy's idea. And also read the rules. It's like really important to read the rules, because when you think of a design, you don't want to be wasting time on a design that's actually not legal in this year's game. So for this year, you've got 12 inches of extension. If you come up with a design that extends 13 inches, that's just not allowed. And so if you prototype that, you're essentially wasting your time. Day 1, so we meet the day after. So the game will be revealed. We will watch that as a team. We'll have a party pretty much. We'll watch movies up until the 2 a.m. time when it's released. And then we will all go home at about 3, 4 o'clock in the morning, sleep through that day, get some rest, and come back the next day, which is typically a Monday, right? Yeah. When we meet then, we'll have a rules test so that we know that everyone knows the rules and we don't get illegal ideas. Then as a team, we'll sit down and we'll talk about and analyze the game. So are there points that are easier to score than others? Are there ranking points that are easier to get and more worth your time? That kind of thing. Like what's going to be really important in the game? Defense, is that going to be an important part? And then we'll discuss overall robot strategy. So identifying what we want to do as a team and what we want our robot to do. So we want to shoot the balls in the high goal, is like something you would have in your robot game strategy. And you'll have a list of your top priorities. So in the bottom left of this slide is our robot priorities from 2019. So we wanted to self-climb to the level 3 hab, and then we wanted to collect hatches from the loading zone. Then we wanted to lift the hatches up to all levels of the rocket. And then equal last was hatch ground intake and a ball ground intake. So you want to have that priority list so that you don't end up making something that compromises the others. So say our ball intake, we need to build it around our hatch intake and it hinders our hatch intake. Well, collecting hatches is higher than collecting balls, and so we'll have to nullify that and redesign the ball intake so that it doesn't hinder our hatch collection and hatch delivery. And then the robot will board. So robot will board is pretty much the criteria of what your robot is going to do. So it's not the same as the robot strategy, it's what your robot will do. So it will shoot balls in the high goal at 5 balls per, at 1 ball per second, say. So it's laying down the ground rules of what you're designing your robot around. And then the next day, we've got the how. So we will break into teams of 4 or 5, making sure that they're from all over the place. So we'll have awards team, electrical team, mechanical team, all in the one little tiny team of 4 and 5. So we have members from all aspects of FIRST, and with them, they bring their own ideas. You want to brainstorm all ideas that are legal, of course. Any idea, like there's this saying, if it's stupid, but it works, it ain't stupid. And so you want to get all ideas out there. For example, in 2019, we played around with the vacuum cleaner, sucking up and attaching to the balls and the hatch panels. We thought that was absolutely stupid, but then we get to Worlds and 971 Spartan Robotics have done exactly that. They've used vacuum suction to collect their game pieces, and it's just worked absolutely amazing for them. So yeah, you want to get all your ideas down in those little sub teams. And then you'll regroup as a whole team, and each sub team will share their ideas with the whole team, and we'll write them on the whiteboard. So this is a whiteboard from this season, I believe. So we have all of our ideas for the end game on the left there. Then the blue says shooting. So we have all our ideas for a shooter. Then we have the spinner. So that's the color wheel. We have all our ideas for that, all of our ideas for the intake, and all of our ideas for the indexer/hopper. So we've written them all on the board and broken them down into their subcategory, like mechanism categories. So yeah, that's the how, what we'll do on day 2. And then after that, we'll research on days 2 and some of day 3, because by the end of day 2, we've just finished the how. So one of 1678's golden rules is steal from the best and invent the rest. So this means look at robots from previous games that had similar tasks or game pieces. So especially for this year, I know we looked back at 2012 and 2016, who both had foam balls. In 2012, you could only hold 3 of them, and they were about the same diameter as the power cells this year. You can also look for inspiration from real world scenarios. So in 2017, 971 looked at a paintball gun, because you had to shoot a lot of balls really quickly. And with a paintball gun, it does exactly that. So they designed their robot around a paintball gun, pretty much. We also have, I spend way too much time on YouTube looking at robot reveals from all aspects of FIRST, all years, all levels, FTC, FLL, FRC. And so whilst I've been doing that, I thought I may as well make some use of it. And I've put playlists together of intakes that I find are really good. So if I find something that's unique or really good, I'll put it into a playlist of that mechanism. So shooters, intakes, hoppers, climbers, that kind of thing. And so our team uses that as a resource to look for inspiration for our designs. And then, yeah, so if you have issues trying to figure out your ideas really late, later into the season, maybe week 2 or 3, if you still haven't really got ideas, RI3D is robot in 3 days. So in the US, they have a whole bunch of university students work together to create a robot in 3 days that can complete the task for that season. They're on YouTube. They're really helpful. And the Open Alliance is a bunch of teams on Chief Delphi, which is a chat forum for FRC pretty much. And they're also really helpful. So you have teams like Spectrum, Frog Force, and Rembrandts, I believe, are the 3 main ones that I can remember that do Open Alliance, which is they share their entire build process from day 1 up until the end of the season. So if you're really stuck, you can go there and look at what they're doing for inspiration. I missed the point. So try and get a video or research each mechanism that's on the whiteboard so you can get a better idea of how it will work. So then you can properly decide. So picking the best few. You want to whittle the list down to 2 or 3 mechanisms for each subsystem, because I'm assuming you don't have infinite manpower. So we'll whittle it down to about 2 or 3 for each subsystem. So for an example, with intakes, you can use belts, wheels, or vacuum suction. So that's 3 mechanisms that you can then go prototype. So you want to have a wide range of different prototypes so that you don't limit yourself in ideas from the beginning of the season. Because if you do that and your ideas don't work, then you've already narrowed it down and you have to go all the way back to the beginning to start prototyping again in, say, week 2 or 3. And as you're picking them, you want to remember your strategy and your robot wheel board. as well as the rules, so that you don't make illegal mechanisms, and you don't want to start making something that your strategy doesn't agree with. So you don't compromise your strategy or compromise your robot constraints that you've set at the beginning of the season. We use a decision matrix to help us determine the best mechanisms. So there I have an example for the intake this year, I believe. So we have a bunch of criteria down the left-hand side. We want it to be robust. We want it to be touch it, own it. So as soon as our robot touches the game piece, it's ours. No one else can take it. Avoid having more than 5 balls in our robot. Packaging, so how big it is and how simple it is. And then we have a weighting. So we've figured that robustness and touch it, own it was more important than packaging. So we have given a weight of 5 to robust it and touch it, own it. And so that multiplies the number under each mechanism by the weighting to get the total amount. And then we'll add it all up to get the overall total. So 118-2012 is the intake that Robonauts used in 2012. We decided that was one of the things we might want to look into. We added up all the criteria and we got a total rating of 75. An over the bumper intake was 78, an active funnel 76, and then a 4-bar over the top, like with a top roller, was 74.5. Oh, and I've only just noticed now there's vacuum on there, which has been given a value of 1,000 for every category. And yeah, you want to base the decision matrix off of the videos you've watched and the research you've done into these mechanisms, not just an arbitrary, oh yeah, we think it's going to be touch it, own it, or we think it's going to be simple, because inevitably it probably won't be. So after we've picked the best few, we allocate the prototypes to smaller teams. So same as your brainstorming teams, you want to have teams of all skill levels. So rookie members, senior members, and people from all fields. So mechanical, electrical, awards, CAD. You want everyone to be working together in a different team, in each team. So you might have 2 prototypes for each team. You might have 1, depending on how many people you've got. And some more complicated prototypes might require assistance from senior members or mentors. And one of the most important things is you want to make sure that the sub-team you've assigned a prototype to actually wants to build it. If you have a team that hates what they're doing and doesn't want to build it, then they might just make it fail, or they won't work as hard as others to develop it. And so you won't get a proper prototype that could eventually actually be the solution to your problem. So that only takes a short amount. So on day 4, we do design. So mainly it's pencil and paper sketches with rough values for measurements. You can reuse sketches from the how discussion. So when you've broken off into smaller teams and discussed how you might do something and how a mechanism might work, you probably have some scribbles down to help explain other things. And so you can base your designs off of that. More precise mechanisms might go to CAD first before you start actually putting pieces together. Once an initial design has been created, we move on to production. So we use a whole bunch of wood. I'll talk about that later. And space is limited. So each mechanism can't just be the size of the entire robot. You need to leave room for each individual mechanism. And then you also need to leave room for the handoff between each mechanism. For example, a shooter that works really well is completely useless if the hopper you're storing your balls in can't actually deliver the balls to the shooter. And you want to design for adjustability so you can change variables quickly and test as many as possible. So for example, a shooter, you want to have the hood be able to adjust so you can quickly change the angle and test as many angles as possible. The example I have up there is from 2017. We have a board and we wanted to test the best angle to deliver a gear on. So there's a little post at the back and there's some nails on the bottom board there. And so we just lifted that up and moved it to each of the nails to get a different angle. Yeah, this is what I was talking about before. So wood is pretty much your best friend in prototyping. So when you're starting to actually put pieces together, it aims more towards the concept selection. So remember before I was talking about the actual decision of mechanisms. So flywheel versus catapult, 4-bar versus elevator, that kind of thing. So we have a whole bunch of wood left over from the field elements, and we're lucky enough to have a big storeroom, so we store a lot of scrap wood as well. And so we have a whole bunch to work with and can pretty much build anything we need to. The prototypes, you've got to remember they're a proof of concept. They don't have to be precise. Like if you have an intake, of course you don't want it to be on a 45-degree angle because it's not going to be effective at all to prove your concept. But they don't have to be like to the micrometer accurate. And yeah, so some teams that have access to a laser cutter will precisely cut their prototypes from wood, and they generally will CAD all their stuff first and CAD their prototypes before even touching the wood. And then they'll CAD it, send it to the laser cutter, cut it out, assemble it, and test it that way. We don't have that. We just use hand tools pretty much. So our prototypes are all pretty rough. So the next thing you want to do is test your prototypes. So we use trolleys a lot. So we have 2 trolleys primarily. We will put our mechanisms on a trolley to test them, and then we also have like a fake bumper piece that we clamp to the trolley to resemble like the robot actually doing it. So the trolley one is here. I'll full screen it. Sorry, it's on an angle. I couldn't figure out how to rotate the damn thing. But so that red bit back there is a fake bumper. And so we will just attach with clamps, or this, I think this one's actually screwed into the trolley. And so we'll run it and just push it into the game pieces to act like our robot driving into it. How do I get out of this now? I can't hit escape. All right. So in that video as well, I was holding a drill to a piece of hex shaft to actually power the intake. So we use drills a lot to power our stuff with a hex adapter for 1/2-inch hex, but we also use power guns. So a power gun is a drill that has had the motor ripped out of it and then the leads. So this is a cheap drill from Bunnings. We have pulled the motor out and attached leads directly to the trigger. And so that way we can power any of our DC motors off of a 12-volt battery that's rechargeable. So you can see here, he pulls the trigger and it spins the wheels that we use for the color wheel initially. And then you can also change direction as well because of that toggle switch that the drills come with. It also allows you to vary the speed slightly by pulling the trigger more or less. Andrew, oh wait, no, I can actually exit full screen now. So yeah, we use power guns and drills quite a bit. So you want to put your prototypes through like not ideal and failure scenarios to see where the weaknesses lie. So you want to knock them really hard and see if they break, because in an actual game, your robot's going to be ramming into walls and other robots and stuff. And if it breaks with a small tap, then it's obviously not going to be a great design for you to use. And you want to get them to the point where they can quickly and reliably complete the task. So you want to be testing and testing and testing and tweaking and tweaking and testing and tweaking until you get to a point where they can do what you want them to do fast and reliably. So this is testing our shooter, and you want to do it as much, like you just want to keep repeating it over and over and over. So you can see we just keep returning the balls back to the shooter, and we just keep testing it for I think this was about 40 seconds, but we continued after that as well. And you also want to record your results. So on Mythbusters, Adam Savage, he said that the only difference between screwing around and science is writing it down. So if you're not actually writing down your results, you're pretty much just screwing around, and you don't really want that. So ways that we've recorded our results is we have high-speed video, so slow motion. Most phones can do it these days. We take a lot of photos. We record what we do in a day and the values of so this test, we would have recorded how many went in, how many we put through to get a percentage of how accurate it was and how many made the distance, how many fell short, how many went over, that kind of thing. And we also have a build blog. So we record what we do every day, what each sub-team does every day, and then we're able to refer back to that when we go, wait, what did we do yesterday? And we'll go back and we're able to see exactly what we did. So yeah, test. So once you've tested everything, you might want to move on to a higher fidelity prototype. So sometimes you require a higher fidelity to achieve the goal of proving a concept where wood is undesirable with like the required properties. For example, this year, the indexer, so our hopper mechanism, the wood was the coefficient, like the friction between the balls and the wood was too high. So we had to switch to polycarb to actually test whether our mechanism was going to work. So again, we're lucky enough to have a really big storeroom. So we keep a whole lot of scrap from build seasons previously. So we have a bunch of scrap polycarb and a bunch of scrap aluminum tubing. For high fidelity prototypes, teams like to use 1x1 aluminum extrusion. So this is what Rev sells. It's T-slot extrusion. So you can put a bolt head in the T-slot, and then you can bolt things down to it and slide them around to different distances to get the right distances. And it's also really good with the like testing all the different variables. So you can move your shooter to a different spot or move your motor further away to have a better gear reduction and stuff like that. And Vex VersaFrame is also really good. So you've got the tubing that they sell has holes every, I think it's inch. I think you can get it every half an inch as well. Their brackets have the same holes on them too. So they're really quick to swap out, move them around, pretty much like metal Lego. Oh, Meccano, kind of like Meccano. And then they also have gearboxes and shafts and stuff like that you can put through. So this motor is attached to a bracket that sits in the aluminum, in the holes that they have there. This gearbox here clamps over the tubing. You can loosen it, slide it to a different position, and tighten it back up again. And at this stage, it's more aimed towards parameter evaluation. So flywheel speeds, shooter hood angles, compression in a shooter, so the compression between the flywheel and the backboard. What else? So yeah, the high fidelity prototypes allow you to prove things where you can't with wood, or you want to move up to the next level to test your idea in the way it's going to be presented on your robot made out of metal and polycarb. So once you've done your high fidelity prototypes, you want to finalize your design. So as a team, we will sit down and do a design review. So we do this pretty much at the end of every week or the end of every couple of days. We'll do a design review where we will sit down, look at our design, and review each mechanism. And we'll look at it like, does it achieve what we've set out to achieve? Does it meet the criteria that we set out to like meet at the beginning of the season with our robot wheelboard? So we will look back at the robot wheelboard and we'll go, hey, does our shooter shoot more than one ball per second? Because that was what was on our board. Does it do that? If it doesn't, then we'll have to go back and keep reiterating it until it does. So you want to be able to go back through your design, have a look at it with your entire team and go, hey, does it do what we want it to do? Does it actually complete the tasks of the game? Then once you're happy with your designs, you want to CAD. So throughout the entire design process and prototype process, you want to be communicating with the CAD team so they know exactly what's going on. And so they don't send out something to be made when it doesn't actually work. So if your prototype works really well off the bat, then you might not even have to change anything. The CAD guys can just go up and measure it and take it back, measure it, put it into the computer, and they'll have a model that's already working. And then you can just change the materials to whatever you make it out of. And yeah, after you've designed, you move on to manufacturing of the final parts. So our team uses primarily hand tools. So we've got one member here with a hacksaw. This is actually me on the belt sander. And then we have another team member who's using the jigsaw. So we primarily print out on large sheets of paper our designs to cut around. So we have an Officeworks nearby that we go to, and we can print really large on that. So over here, this is a full sheet of polycarbonate. And on there, I don't know if you can see clearly, but there's paper cutouts. And so with the jigsaw, our member here is following the lines to cut out exactly what we need. On this here, the bracket I'm machining is a piece of paper as well. So we stick it down with spray adhesive. And so it has all the bend lines that we need, all of the holes that we're going to drill, and the outline of the piece itself. So we can sand it down to the exact right size, then bend it, and then drill where we need to. You can also send it off for machining or machine it in-house, depending on your team's capabilities. So this year we were lucky enough to have a place water jet some lightning holes for us. So we send off our parts and designed to be machined by them. Also, you don't be scared to iterate after your final designs. So you don't want to spend too long in the prototyping phase. If you spend 5 weeks in the prototyping phase, then you only have 1 week. Well, actually, no, because build season isn't 6 weeks anymore. They've removed bag. But you don't want to spend too much time in prototyping. So if you spend up to the week before competition prototyping, then you won't have enough time to actually put your final robot together. So you want to be able to have your final designs done so that you can tweak them and do that, like flywheel speeds, being able to tune those to work properly, making sure that all your mechanisms fit together and are integrated properly. And yeah, you can still tune them after they've been finalized and manufactured. We actually did that this year, and we pretty much always do it every year. We have our final designs, we put it all together, we get it going, and then we go, oh wait, this thing isn't working as intended. And then we'll tweak it, redesign it, remanufacture it. And we'll do that probably a couple of times maybe, or a few times each season. So yeah, that's all of that there on our process and how we do things. So I've got some videos and stuff of our mechanisms and prototypes throughout the years. So this is the initial prototype. I can't full screen it because it's hidden. Whoops. This is our initial prototype of the climbing mechanism that year. So you had to climb a rope. So we have PVC pipe taped to some wood that's attached to a drill with weights on it. So this thing's made entirely out of wood, has a drill powering it, and is all taped together. This here is our higher fidelity prototype. So we have a metal bar here. It will flick up to trap the rope, and then we spin it to go up with some surgical tubing to spring load this metal bar. And again, it's powered by a drill on the churro. So that's our 2017 one. So in 2018, we have our lifting mechanisms. So we have, this is just an image of the elevator we mocked up. So it's just a bunch of draw slides screwed down into wood with wooden pulleys and stuff. That's one of our team members just posing next to it. This one up here is our double reverse 4-bar prototype. So again, it's fully made of wood, just with some screws in it, or I think it's holes with bolts because they need to pivot. And so Isaac's just walking through, showing that it'll go up and keep flat. And then this here is actually what we kind of ended up going with. As you can see, it's very roughly put together. There's wires everywhere. There's weights taped to the end so we can see how much weight it takes. But yeah, that's the initial prototype, or one of the initial prototypes for that. We have our wrist there as well. It goes up and down. So this is 2018, our arm mechanism. So that's what we ended up going with, 4-bar there. So also 2018 is our intake mechanisms. We have these 2 wheels, a wheel here and a wheel there, just shot it through so that could suck it into our robot. And then we also have this here, little weird mechanism that could also suck it up and in. But the photo is what we ended up going with. It's not a great one, but there's 2 arms that are out and then they clap together. And we called it the clapper. So that's our intake. So for 2019, we have some ball intake. This is the very first prototype. It's just wood clamped. Oh, whoops. Hello, go back. Okay. It's just wood clamped to a trolley with holes where there's hex shaft and the wheels go. And so we're just pushing the ball into it to see if it'll work. And it worked pretty well. This is another video of it later of just shooting it up into the cargo ships to show that we could deploy it. And then this is what I was talking about before. This is us playing around with the suction. And so we have a couple goes with the ball, and then we move on to the hatch panel as well. So we have the hatch panel stuck on, albeit not too well, but yeah, we played around with it for a bit, which was quite fun. This is probably the one of the more documented things we have. So this is our hatch intake mechanism for 2019. So this is the initial prototype. It is a wooden board with someone sitting on a trolley, and the wooden board has Velcro on it that could attach to that. The white ring on this game piece was made out of Velcro as well. It was the loop side, and so we put the hook on the wood. And then we moved to putting pneumatics into that wood. So we just got the 2 pistons, drilled holes for them, and mounted them on there and played around with that. Then we moved on and we tried out a ground pickup mechanism, which worked pretty well with a person. And then so this is a claw that went on the inside so that we could secure the hatch panel better than just Velcro. And then we went and tested it more with different angles. And on this one, there's a connection between the 2 pneumatic pistons. There's this square shape. And this is us going to the extreme and testing it on a 90-degree angle, and it worked. So you can see the big metal square that's made out of just scrap bits of metal bracket riveted together. And then this is what it ended up looking like. We had a beak inside here, Velcro on the top, and a pneumatic push-out mechanism made of polycarb. And you can see the beaks there, the hooks that came out. And then, so this one's probably more relatable to everyone here, the 2020 intake mechanism. So we started off with just a singular piece of churro attached to a drill with a whole bunch of wheels on it. And with the trolley, again, we've got the trolley and the bumper is clamped onto the trolley so that it simulates a real robot front. Then we moved on to the full mechanism, which was, so it slid out from underneath our robot. Then we spun up the wheels. And then it slid back in. So again, this is all made out of, pretty much all made out of wood, except for the chain and the draw slide. We had the whole thing sliding on. So it slides out on draw slides either side. Then we upgraded it with some more wheels to suck it up to the correct height. So with our robot, the balls needed to get up over this height to be able to go into our hopper. So we sprung it back so that it could go flush when our robot went back into the frame perimeter. So it worked pretty well. It sprung up to let the balls through and then sprung back. And then we upgraded it even more. So again, on the trolley, it started flat so it could fit underneath our robot. And then when it came out, and yeah, the balls flung up and kind of hit me in the face, but safety glasses. So again, it's all just powered by a drill and it's all made out of wood. So wood. The only metal bits are the draw slides that it's on, the axles for each of them, and then there's the plastic pulley wheels between them and the bearings, of course. But yeah, that all then led to our final design, which slides in and out from underneath the robot. We have our fake bumper here again. And then as the balls come in, they get sucked up and this is sprung back. And even if a ball gets stuck, it gets pushed in. So this is us just making failures, putting it all the way over to one side, seeing if it gets sucked in. But yeah, so this is pretty much the end product, the final design that we were just testing, and we've kept tweaking it since, so that we didn't get these kinds of failures. So that's the 2020 intake mechanism. And I think, so that's it for the PowerPoint. Oh, I need to unshare the screen now. Okay, cool. But yeah, I'm gonna show you some physical prototypes that we have for elevators. So we decided to go with an elevator to help us climb in the 2019 season. And then that led us to use elevators again in the 2020 season to climb. So this is the first initial prototype we had. It is a large piece of tubing with a slide in out bit that's made up of two pieces of 1x1 tubing bolted together. And then there's some bolts down the sides to keep the tubing in place to stop it wobbling around as much. And there's this massive slot cut down the side of the tubing to allow for the bolts here to slide in and out so that the piece could slide straight. But yeah, that was our initial very first prototype, because again, making something like this out of wood wouldn't work. So we had to move on to higher fidelity prototyping to actually get to what we want. So that's the very first iteration. And then we moved on to our second iteration. So this one uses bearings in the end here. In the end, we have bearings to keep it center and to reduce the friction. We also have bearings on the side here. And so those help it to slide. I don't know how well this is going to still work, if at all. Looks like it's not going to work. Oh, there's a pin that's come out. So yeah, we would pull on this strap, which is attached to the very back, and it would go up, pulling our robot up, allowing us to climb. So these bearings were pretty much the second iteration. Then we moved on to the third iteration, which ended up being actually our final design. We have this red ratchet strap connected to the top. We had a spool pull on this, which then lifted this entire mechanism up. And we have the wheels on the bottom to help us slide. So we've got bearings in the side here, which reduce the friction. And again, we have bearings on the inside of the inner tube to help reduce friction at the back and to support it, to stop it from wobbling from side to side. So that's the end of our 2019 season. And then in 2020, we again wanted to use elevators to climb. And so we iterated again. And for this year, the bearings didn't fit with our profile. So we needed a lower profile, we needed a lower profile design to help us out. And so we've used nylon pieces. We've used nylon inserts into the tubes in place of bearings. So it still reduces friction and also reduces the bend. So these do not bend very much at all. If we try to bend it up or bend it down, there's not very much bend at all. So that's our final iteration for now. We're probably going to iterate more on it because the attachment method for the nylon was glue and screws and it didn't work too well. So we keep iterating. But yeah, that's pretty much it for this presentation. If you've got any questions, drop them in the chat, and feel free to contact me. My email address is on this final slide here. It's not being showed, but yeah, that's okay. It's just lewin.mulvihill@gmail.com. You can watch back the video to find it. But yeah, that's pretty much it.
Awesome. Well, we have a couple questions for you.
Right.
The first one is, what CAD software does your team use?
So we use IronCAD. So IronCAD is behind me on the banner here. We primarily use this because we had our head CAD person had experience with it from FLL. He did a CAD model in IronCAD for one of his FLL projects. And we've just stuck with it ever since because that's what he learned to use and that's what he's taught us to use. And so that's just ended up being what we use.
Okay, I love this next question. All right, you ready? If you stopped suddenly, wouldn't all of the balls in the hopper just fall out?
Yeah, so we have a separate mechanism that hadn't been designed yet that would move up and down with pneumatic pistons to stop the balls from falling out.
Okay, so, this person was clearly watching very closely. I love that.
Yes.
Do you have a process document for your season that's built on each year?
So each year we have our build blog that we record everything we do on. So it's a day-to-day recount of what we've done. And we also iterate on our process each year. So this year we implemented a Gantt chart, is it? Oh, Zach's handbook, yeah. So one of our members has put together a small handbook that details motor ratios and how to use all these separate bits and bobs. All our different processes in it. So we have a small little A5 handbook that details all of our processes and what we follow to do what we do.
So I think the follow-up question would be is that available to the rest of the FRC community?
I don't know. Andrew said he'll have a look. We can contact Zach and ask him if he wants to put it out there, but I'm pretty sure it will be able to. Yeah.
Awesome. And here's a really timely question. What would you do and how would you prototype if you can't meet right now due to COVID?
So some of our prototypes this season, some of the initial prototypes were actually done with Lego. So if you have access to Lego, you can just play around with that and see if you can get that to work, and just take photos, videos, and document what you do. And then when you are able to meet, you can look back to that documentation and start from there and upscale the prototype to be made out of wood or whatever you're going to use next. You can also have design meetings over Zoom, where you can share your screen and share sketches or videos that you found of mechanisms and that kind of thing with each other. And so that way you can get a start on the design process and getting your initial designs before even going into the workshop and getting hands-on with tools and materials.
Excellent. Well, Owen, that was a fantastic presentation. Thank you so much.
Thanks.
Anything you have to say in closing?
Not really, no. Thanks for watching. Yeah, fail fast, fail cheaply is our motto. I guess also 1678's golden rule. Learn from the best, or steal from the best, invent the rest. So watch videos of robots from previous years that relate to the game. So for example, this year there was 2012 and 2016. What was the other thing I had in there? If it's stupid but it works, it isn't stupid. So write down all of your ideas. Any idea is a good idea as long as it's legal by the rules of the game that year.
Excellent. So we have another question that just popped up, which is great. How do you budget your robots?
Pardon?
How do you budget your robots?
So each sub-team will write down how much their final design will cost. So we're lucky to have a lot of scrap materials. So our prototyping process is generally done entirely out of scrap. And then we will assess how much money we have to put aside for the robot. And then each sub-team has the list of parts, where they're from, how much they cost. And that gives us a general idea of how much each subsystem is going to cost. And then we add it all up to find out how much the entire robot's going to cost. And generally, we have to be below the 5,000 US, but they've removed it for this season.
Great.
But that generally hasn't been an issue for us.
Awesome. All right. Well, thank you so much again. This was an awesome workshop, a great evening. We also have to always thank the people behind the scenes here. So a huge thank you to Andrew and Lyndall Clark, who are down there with you. Yeah. They are always there helping out.
Andrew's here and Lyndall's over there.
Yep, from Project Bucephalus, a huge thank you to them. Also a huge thank you to Ian from IC Robotics, who's been helping out behind the scenes tonight as well. And I hope you all have a great rest of the evening. Have a great week. And we'll see you all next week. So take care.
Good night, everyone.